Hello, everyone, and thank you for joining us today. My name is Michael Evangelista, and I will be your moderator for this webinar. Just few reminders that you are in listen-only mode to avoid unnecessary background noise. However, you can type in your questions anytime you want, and those questions will be answered by our panelists in the Q&A segment. The recording and certificate of this webinar will be sent out in 2 days' time, and our topic for today is about the uh, grounding resistance, alternative grounding resistance testing, and it will be presented by our expert from US. So without any further ado, let's start the webinar. Grace?
Hi, everyone. Thank you for joining us for our webinar today. I'm Meredith Kenton, Megger's Digital Marketing Specialist. As always, if you have questions about webinars, feel free to email me. I'd be happy to help you get things figured out. And if you have questions during today's presentation, I ask that you submit them on the panel. It should look just like this one, and it should be on the right side of your screen. If we don't get to your question at the end of the presentation, we will get you an answer via email after the presentation is over. So don't worry if your question isn't answered. Today's presenter is Jeff Jowett. He's our Senior Applications Engineer. If you have questions that come up about ground testing after the presentation, feel free to reach out to him directly and he'll get back to you. And on that note, today's presentation is alternate ground testing methods, and I will give it over to you, Jeff.
Good day, everyone, and I want to thank you for attending our webinar. So let's get started. There's a lot to cover. Next. We'll start with two basic definitions of testing that you do in grounding and with a ground tester. Resistivity and resistance, two very closely related terms, but with very distinct definitions and applications. So we just want to make a quick mention of those two. Last week, we did resistivity, and that is the electrical properties of the soil itself, independent of any human interaction. And you use resistivity measurement primarily for locating and designing a grounding electrode. Now, once the electrode is installed, then you go to resistance measurement. And so resistance is what is the capability of a grounding electrode. And by that, we mean anything from a rod to a quarter-acre grid. They're all pretty much the same. It's just more metal in the ground for the purpose of establishing a low resistance electrical contact with the soil. Next. And why do we want to do that? Just a quick mention. Grounding is done for the purpose of protection of human beings and your electrical plant or your electrical facility from problems on the system, which pretty much consist of things like lightning strikes and surges, voltage spikes, and so forth, surges on the utility, which get into your system, and you want to be able to divert them quickly and safely back into the soil so they can go back where they came from and not resonate around in your electrical system, do damage to equipment, and also create potential gradients for human beings who accidentally come in contact at the wrong time. So we're going to look then at a grounding electrode and how do you test that in specialized situations that are particularly demanding. Next. So these are a list, and these are not all of them, but this is a list. There are quite a few different methods for testing a grounding electrode. That is to say, a ground rod or a ground grid or whatever it happens to be. From the standpoint of testing it, it's all pretty much the same. And in our webinar of fundamentals, which was a few weeks ago, we talked about the top three. Fall of potential is the method to use. We've already reviewed this, but if you didn't happen to be online for that one, just contact me and I'll be glad to help you with it. So if you can, fall of potential is always the preferred method to use. Then simplified or modified fall-up potential. That's just the same thing, but with a few steps condensed to save time and time and energy. And then the 62% rule, that is the real quick one where you just take one measurement, but there are limitations on where you can use it. So we've already discussed those in our initial webinar. And today we're going to look at some specialized methods, 5 of them, that deal with difficult situations. And bear in mind, there are other methods besides these, but these pretty much cover the core of insulation resistance testing in difficult situations. Next. And this is the problem that you're trying to overcome. This is where you have limited space and you can't get your current probe out far enough. So bear in mind that when you're doing your test, you're connecting to your ground that you're trying to measure, and then you're going to put a potential probe usually as far away as you can get it. And the point of the potential probe is to just set up a test circuit so that your tester has an electrical signal to recognize and make your measurement. Now, the ground that you're testing, the electrode that you're testing, has an electrical hemisphere around it. This is referred to in the literature as remote earth, or in other words, what is the volume of soil around your grounding electrode that is determining the resistance that fault current is going to see as it tries to go to ground. And obviously you want that resistance to be as low as possible so that your fault current can get safely into the ground and it's not up in your electrical system doing damage. And so if you're working in tight environs, now your current probe will also have its own hemisphere around it. And that if that overlaps with what you're trying to measure, then let's say you're trying to do a fall-up potential test and you're plotting your measurements and you just see a line that keeps going up like this, you can't submit that as a test result. If you're a testing service and you have to submit your test results to a client and you submit something that looks like this, the client's not going to accept it because you can't tell on that graph where the resistance of your test ground stops and maxes out, and where the resistance of your current probe, which is irrelevant, where that takes over. So next. So we're going to start then with the most commonly used method for situations like we just saw, where you can't get your current probe far enough away to do a fall-up potential method. And that would be the slope method. And this is pretty much the method preferred by the utilities in most cases because it's relatively easy to use, and utilities have a big problem with because they have relatively large grids under substations, and then they're also very often in kind of urban or build-up environments. So utilities have a big problem with trying to get enough distance to get their current probe far enough away to do a fall-up potential method. And so in lieu of that, the method that they most often use is slope method. Next. So here's what you're doing in a slope method. Your tester, in this case we're showing a 4-terminal, but you can do this with a 3-terminal as well. You're connecting onto your grid wherever you can get it. And generally, the procedure which we'll be using throughout this presentation is you're just going to connect onto your grid wherever you can physically connect to it. Just, an easy point of contact. And we work from there. And then you've got your current probe run out, usually as far as you can get it. And now your potential probe in the middle is going to be walked in intervals, and a series of measurements are going to be taken. And the darkened probes that we show here are the critical distances that are going to be used in the mathematical proof in the slope method. But we also show all those other positions, the kind of ghost probes that we show there. They are to kind of augment your test procedure, and we will see why on the next slide, I believe. Next. Yes, okay. So you're taking a series of measurements and you're plotting the resistance against the distance at which the measurement was taken. Now, you notice here your measurements are going to kind of keep creeping up because they're going to go into the electrical sphere of the current probe. And if that didn't happen, then you'd have a fall of potential graph and you could stop there. You wouldn't even need to do slope. But what we're showing here is that if you take a series of measurements, then it's a good idea to do that. In the interest of time, you don't have to do that. You can work with the three critical measurements, which are 20, 40, and 60% of the distance to the current probe. Those are the critical ones that you're going to use. But it's a good idea, if you have the time, to take some extra ones and do a plot like this. And that serves two purposes. One is that it gives you confidence that you have a reasonably good test setup. If you get a sawtooth pattern, that tells you that there's too much interference going on with your test. Stop right there. Don't continue to waste time. Pull your current probe up and go off in another direction or something like that and start over again. But if you get a reasonably smooth curve like this, then you can come back to this later on and use it. So next. Now we're going to look at the mathematical calculation. We're not going to go into this in detail. If you need that, I can help you separately. But for the purposes of this webinar, we're just going to go over it quickly. You're going to do your initial mathematical calculation, R3 minus R2 over R2 minus R1. This gives you a value that's called the mu value after the Greek letter that's used. And then you're going to take the mu value and you're going to use that in tables that you can find in the literature, and we can provide them. The mu value, you look across on your table, and that gives you what is called a slope coefficient. This is based on simplification of calculus, rate of change of slope. The distance to your potential probe over the distance to your current probe. And that equals a mu value that you find on the table. And then with that, you know what the distance to your current probe is, and so now you can calculate for the distance to your potential probe. And then that tells you where your 62% value is on that little graphic that you made. And once you've done that calculation, you know where to place the potential probe and get your accurate reading. And so there are two things that you can do at this point. If you're on site, you take your potential probe out to the calculated distance and take a reading, and that's your reading. Or if you've gone back to the office, but you've made that little graphic that we just saw, you can go onto that graphic and read your potential position off of that graphic, and then that is your test result. And if the two agree with each other, then that's a good confidence builder in the reliability of your test result. Another confidence factor, just to keep in mind, you may not find the slope coefficient. Your mu value may not be on the provided industry standard tables at all. And if that happens, then that tells you, okay, your test setup just didn't work. You have to go back and start over. Most likely that will happen if your current probe is contained completely within the electrical hemisphere of your test ground. And that can happen, especially with very large grids and with very bad grounding conditions where the electrical hemisphere of your grid is really large and your current probes, that its own test field is contained completely within that grid. And so you won't find a mu value on your tables. Tells you to start over again and try it again. So next. And so what we're seeing here then, this is what you're looking for. The red vertical line indicates where your hemisphere, electrical hemisphere around your test ground maxes out and achieves its maximum resistance. And the current probe hasn't, its own electrical field hasn't taken over yet. So that's what you're looking for, the vertical red line. Next. And so you can do that once and walk away with it if everything seems coherent. But to be thorough, and especially if you're dealing with third parties, it is a good idea possibly to repeat the test in a few directions and with a few different probe spacings. And you want to get test results that fall fairly close together. So test 1 and test 2 are kind of scattered. They sort of tell you that, well, your test conditions weren't ideal, and those results are somewhat in question. But if you'll note that with test 3 and test 4, the results are starting to fall relatively close together. So that's an additional confidence factor. You don't necessarily have to do this, but if you're being entirely thorough, you might want to do that. And then you could simply average the results of test 3 and test 4, which are fairly close together to begin with. And that would be a pretty good, pretty reliable test result. Next. So the advantage, it's a way of dealing with tight testing conditions where you don't have a lot of room to work with. The disadvantage, of course, is that it does lose some accuracy and requires mathematical interpretation. Next. So now that moves us into our next, on our second test method. This is a very difficult method, and it's intersecting curves. It's one that most of you probably are not ever going to need to do. You'll see that it's really quite complex. I hope I can explain it reasonably well. But if you're in a situation where you must provide test results to a third party and you're in difficult environs, then there's a lot of work in intersecting curves. But it is, if it all works out, it is reliable, and you can use it to submit a test result to a third party in difficult environments. And the principal variable that we're trying to deal with here is the 62% method, which we mentioned in our initial webinar. If all conditions are ideal, then 62% of the distance to your current probe is your ideal measurement. But bear in mind, this requires ideality. Well, in a big grid, you don't have ideality because it's 62% of the distance to your current probe from the electrical center of your test ground. And you don't know where that is on a grid. Even if the grid is geometric, like the one on the left, the geometric center does not necessarily coincide with the electrical center. And then what about the grid on the right, where you can't even really figure out a geometric center because the grid has an unusual pattern? So next. What we do in that situation, suppose you tried to do a fall of potential. Well, you'd see something that looks like this. You can't really read from there where your actual limit of your test ground stops and the current probe takes over. You can't find that point on a steadily rising graph like this. But note also on the left side that your graph doesn't level off at the intersection of the x and y axes, but instead it continues to the left. And so what that is indicating is your true electrical center is some distance off to the left, somewhere out on your grid, and you don't know where that is. Next. So now, how do we deal with this? Well, there's a mathematical calculation, which I'm not going to go into in detail, but the distance to your potential probe is 62% of the distance to your current probe plus x and then minus x. We don't need to explain all of that at this point. If you're interested in it, I can give it to you separately. But that's your calculation from your true electrical center. So, next. This is just a quick reprise of the test methods, which I've been going, of the test variables, which I've been going over. So we'll continue on from here. Next. So now what we're going to do is we're going to make a graph out to whatever convenient current probe distance you can find, and we're going to graph those points. And in and of itself, this doesn't tell you anything. But next, you're going to move your current probe to another position, or possibly just another distance, and you're going to do another partial graph. Next. Now, if you're in a hurry, you can probably get away with just doing that twice, but the industry standard is to do this 3 times. So we now have a third graph like this, and next. So the net result now is you've got 3 graphs at different distances and different positions for your current probe. None of them tell you anything by themselves. But now what we're going to do is we're going to go and let's see what's on the next slide. Let's take a look at the next slide. Yeah, this just gives you a summary of what we're doing. So now you're going to make guesses at where the x position is. So in other words, the x is the distance from where you hooked your test setup on the edge of the grid somewhere, the distance from there to your electrical center. Now, obviously, you're going to use common sense. If your grid is 20 feet across, then you're not going to use 25 feet as your x. You're going to make guesses as to where the x may be. And you're going to then calculate the distance to the potential probe based on those guesses of x. And then you're going to go back to those 3 graphs that we just saw, and you're going to calculate from those graphs what the resistance reading would be at that arbitrary guess point. Okay, this is complicated, I know. Bear with me. Next. Now, you're going to do a second series of 3 graphs based on the calculations that you made from your first series. So note, these are 3 more lines that correspond to the different probe spacings that you used. And now what we have is the guesses on your x-axis. These would be the distances that you guessed for your x value, and the corresponding resistances for those positions that you read off of the first 3 graphs. And so the point here is that somewhere on those 3 lines, there is actually the correct resistance reading at the 62% point. You don't know yet where that is, but it's got to be there somewhere because you picked various guesses across the reasonable range of distances. And so the 62% is in there somewhere. And what's going to happen is the, the only point at which these three graphs are going to agree with each other is the correct point, that the 62%, because that's the only thing they're going to have in common. That's the only correct guess. All the rest of them are wrong, but the correct point is going to fall on all three of the graphs. Or actually, like I said, if you're in a hurry, you can do two, and where the two graphs come together, you can submit that as your test result. But in the real world, because of soil resistivity uh, inconsistencies at typical test sites, it's probably a good idea to do a third. And on the blow up there, we see they probably won't fall together exactly. You'll most likely, if they do, that's a good confidence factor, but most likely you will get a small triangle. And so you'll use the center of that triangle. That would be your resistance reading. So that's your 62%. That's the result that you're going to submit as your test result. And if you want to be have an extra confidence factor built into this, you can actually go out to the site and put your current probe in, your potential probe in at that point, and guess what? Your reading is going to agree with the reading that you got off of this graphing procedure. And so that would be what you would submit as your test result. Okay, next. And let's see, I think this is just a summary of the procedure, so we don't need to go over this again. Next. So your advantage is that it's a way of dealing with very tight environs. Uh, the test procedure typically calls for using distances to your C probe. They can't be less than the long side of your grid, and they shouldn't be more than twice the long side of your grid. So note you're doing this in a fairly tight parameter, uh, and the disadvantage is, of course, that it requires a lot of additional work in mathematics. But the advantage of it is that you can get a reliable measurement where your test environment is just very tight and you don't have a lot of room to work in. You don't normally need to do this. Most of the time you'll do slope method or maybe one of the others that are a little easier. But like I said, if you have a third party that's demanding a test result, and against a known procedure, then this is the way to go. Okay, next. Now we go from a very complex method to a very simple method, and this is dead earth or 2-point. And so this is a good one to use. This is a drop dead measurement to use in really congested areas where you just can't find any other method to use. You're down in Manhattan or someplace like that. Okay, next. And with a dead earth, this is also, it's called dead earth because you're going to connect to something, in this case, the water pipe system, which is not part of the electrical system, therefore dead. And it's also called a 2-point measurement for obvious reasons. Now we see here on the older models of test equipment, uh, you can install jumpers to reduce this to a 2-terminal configuration. And so a common method would be to run off of your 2 current terminals by jumpering the potential terminals to them. In the old days, people put in shunts or even paper clips would work. With newer equipment, you don't have to do that anymore. Your new modern testers will, by a selector switch position, will just do the shunting internally. So you just flick your selector switch to a 2-pole position and run your leads out and go from there. So it's a pretty simple test. So one lead goes to your test ground, the other lead goes out to a convenient point of return. So the water pipe system is a good one to use. Be careful. Some municipalities prohibit this. Sometimes the water company doesn't necessarily like this, but as long as you don't have those caveats, it's a good test to use and is commonly done. And so then you just press your test button and bingo, there's your test result on the display. So pretty easy to do. Next. So it's not recommended because it's not all that reliable. It's relying on the return, like the water pipe system, for instance, contributing very little uh, resistance to the measurement, because what you're going to get there is a loop resistance of everything in that loop, which includes your lead resistance and also, of course, includes the resistance of the water pipe system or whatever else you hook to. Sometimes a long row of metallic fence, for instance, can be used. But that resistance is going to be included in the measurement, so the reliability of your measurement is based on that being very low and not contributing very much. But you don't really know that. So that's a limitation and does introduce a potential inaccuracy in the measurement. Next. So where you're going to use this, you can still use it, but it's a drop dead. Uh, it's a drop dead method to use in situations where you need to get some sort of test result, but you just can't use any other option because the obstacles are just so great. But one thing that I should mention is that something that is a little bit on your side in this situation is that the 2-point measurement is mentioned in the IEEE Ground Testing Standard 81. It doesn't endorse it. It does list the limitations to it. But if you have third-party involvement and somebody's demanding that you submit some sort of test result, then at least you can use and you can cite IEEE 81 as at least giving mention to it and defining the limits of the reliability of the test. So it does have some usefulness in that manner. Next. So that segues us into a method that uses a similar test setup, a 2-point setup, but has some uh, built-in checks on the reliability of the measurement. And so it's a lot more reliable than just using a dead earth method where you have to accept what appears on the display and you don't have any flexibility with that. So in this case, we have more mathematical proof built in and we're doing more measurements, but as we will see, let's go to the next slide. In this case, we are going to use a 2-point measurement. And so this is named after the configuration of the probes, which we will see in just a moment. And it's going to use a series of mathematical crunch to proof your test result. Next. So again, this is just a reprise of the 2-point method. This is the method that you're going to be using. This is your test setup, and this is how you're going to be connecting your leads to get your test results, which you are then going to put into a series of mathematical proofs. Next. So this is your test setup. And this is why they call it star delta, because of the appearance of the test configuration. And so note that we tell you that you do want to have your probes out of the electrical resistance area of your test ground. So now instead of going out in a straight line, which is what you do in, I think, just about all the other test methods, in this case, instead of going in a straight line, you're going to use 3 probes in a triangle around your test ground. So note that this is amenable then to a very constricted test area where you do not have a lot of room. Now, what happens if your resistance areas overlap? Well, the bad side of that is, of course, that it's going to invalidate your test. But the good side of it is that the mathematics, they're going to throw out a bad test result. The mathematics won't work. And so at least you won't end up with a bad result and not know it. So you're going to set up your configuration this way, and you're going to do 2-point measurements, and you're going to do all 6 of the 2-point measurements that we see here. So you're going to measure between each of your 3 remote probes and your test ground. So that's 3 of your measurements. And then you're going to measure between the 3 test probes. So that gives you 3 more measurements. So you're going to walk away with 6 2-point resistance measurements. So keep in mind, this is like taking 6 dead earth measurements, for instance. But instead of just walking away with that, you're going to put them into an arithmetic proof, which we will look at next. Okay, so again, that's a simple reprise of what I've been describing so far. Okay, and next. I seem to be running ahead of the time schedule here, so darn, how did I do that? This is your mathematical crunch. So you're going to put those numbers in this, and you're going to do these 4 calculations. And what we're going to see here is if number 1 is well in agreement with the other 3, then that's a very strong confidence factor that your test setup and your test results are reliable. And what you want to see here is a reasonable agreement between these 4 calculations. Now, if they're all over the place and they don't agree, then that tells you, well, your test setup just really wasn't adequate for the job, and you need to go back and move, do whatever you can, work with whatever means you have available, go off in another area and try it over again. But if the test results agree with each other, then you have a pretty good confidence factor that your test result is reliable, and you can submit this as your result and submit it to a client or to a third party or whatever. And now, the point I want to make here, which is really critical to this whole talk this morning, or at least all of the methods aside from dead earth, which is the mathematics. And so in the old days, you had to do this with a calculator, or you had to do this with pencil and paper. And so it was really prohibitive. And it kind of made these 4 of these 5 procedures, which we talk about in this webinar, kind of prohibitive. But now, in the cyber era, this is very much improved and shortened in terms of software. You can now get very easily. You can get software from Megger Company, or possibly from companies. If you're using somebody else's test equipment, they should simply provide you with that. If you have a relatively stripped down tester, then you may not have this capability. But if you have a relatively well-developed ground tester, then you should have this capability built into it, where this method and the other methods that we've looked at, you plug the test results into the software, and bingo, very quickly, you're not sitting there with a calculator and a pencil and paper. Just very quickly, the calculations are done for you, and you have all of this, and you can put it in a test report. You can send it to a client or whatever. So the basic point I'm getting to here is just make sure that you have software capabilities, and don't despair about doing these seemingly complex methods. Most of the complexity comes in the math, and the software will do that for you. And so these methods become infinitely more agreeable to use in actual practice. Okay, next. So star delta, I think I pretty much covered that the test procedure kind of has a built-in proof, and it will throw out bad test results, and so you don't have to worry about that too much. Okay, next. So the advantages, it is a way of dealing with very tight working space. The disadvantage, again, time consuming, but that pertains more to the old days than it does now because the software takes a lot of the time consumption out of it. Next. And so that takes us to our fifth and final method, the fourth one that uses math and software, the four potential method. And this one is particularly good for, again, areas where you have a large grid and especially a diffuse kind of pattern to the grid, and you don't know where the electrical center is. And so it's a way of dealing with the electrical center. Next. So we're making a measurement from the edge of the grid. We don't know where the electrical center is. The mathematical proof is going to take care of that for us. Next. Here's your test setup. You hook on wherever you can. Now this procedure sometimes it can require very long distances to your current probe. So it's not something you're going to try in tight environments initially, but again, if you're working with a large and diffuse substation or grid pattern, then it may be the method of choice. So you're going to, in this case, take measurements at 20, 40, 50, 60, 70, and 80% of the distance to your current probe. So you're just walking your potential probe out and you're taking measurements at those, what is that? 1, 2, 3, 4, 5, what did I say, 6 critical positions. Next. And here we are with the math. All you're doing is plugging those measurements into these formulae and kept making out then a calculation which you want to agree with each other. And next. In this case, let's see, if the first calculation is out of agreement with the others, you can throw it out. You have the luxury of throwing that one out. Again, this is based in the arithmetic, and this webinar doesn't have time to go into the arithmetic. But that is an extra confidence factor. But if it's out of line, you can use the other three, and they still work reasonably well. And so you run them through your math calculations, and again, you don't expect them to be dead on, but they should be within a reasonable agreement of each other, and then that's your test result, and you can submit that as your test report. Next. So again, your advantage, in this case, it's a way of working with diffuse systems where it's hard to figure out where your electrical center actually is, and it makes your probe spacing a little more subjective to conjecture. The disadvantage, again, it's not so much as it used to be because the software will come to your rescue and reduce the time that it takes to arrive at a reliable result. Next. So just a quick summary, fall-up potential is your best and most reliable method. We talked about this couple of weeks ago. And if you were not part of that webinar, then you can get back to me and I can help you with that. So that's really your best method, but it is somewhat time consuming and it does require enough room to get the current probe out of the electrical sphere of your test ground. The 62% method is very easy. That's one measurement, but it is subject to error because at 62% of the distance to your current probe, there could be a water main, a power line, whatever, could be running under that position, and your reading could not be representative of the area. So it has that risk built into it. But it's a good method to use in areas that you've already proved by a fall of potential. So if you're doing maintenance testing and you're familiar with the area, do the fall of potential the first time and then do the 62% rule to save time on subsequent tests. Next. Then, as I said, the four potential method, it's involved, but it's ideal for situations where you're having problems with distancing because you don't know where you have a diffuse grid and you don't know where the electrical center is, hard to place your probes, use for potential. Intersecting curves, a good one for a very tight environment where you must submit a test result. Slope method, you would use that before intersecting curves for the same reason. Tight environment, but you must submit a reliable test result. But if slope method doesn't work, go to intersecting curves. Next. And then dead earth, that's your drop dead method where just nothing else works. You're down on 42nd Street in Manhattan. So you need to submit something, then do dead earth. And finally, star delta, that's like where you're in an area similar to dead earth, but you need to have more reliability in your test result. And so you at least try to do star delta and see if the mathematics work for you. Next. Okay, so we only have just a couple more things to run over quickly. Substation, these are some of the problems that you deal with on substations. Next. Make sure that you have a high-end tester that gives you a lot of resolution on your measurement, because on substations, you typically want to measure less than an ohm, and so you don't want to use an inexpensive, tester that doesn't give you very much resolution. And you also want to be careful of noise rejection, because that's a huge factor in substation. And so you want to get a tester that has very high noise rejection. Next. Okay, I guess we've pretty much covered on these points. These are just quality points to look for in selecting a ground tester. And next. And then these last two slides are basically just telling you that you don't want to take your measurement and walk away. You do want to work your ground resistance testing into a maintenance program, and you want to test on a periodic basis. Next. Because your ground resistance does change over time. I've been to sites where you could go out to the ground rod and they thought they were grounded, and you could grab the head of the ground rod and pull it out because everything below surface level has rusted away. So just make sure that you do have a dedicated maintenance program in effect to guard against any of these potential issues. And I will be glad to help you with any of that. You're welcome to call me. And with that, I thank you for your attendance, and we will go have a few minutes for questions.
Okay, guys, so that's the end of the presentations. If you have any questions, please write it now in the chat box and we'll try to answer it for you. So before going to the question and answer portion, I would like to remind you that there will be a pop-up screen on your when you close this webinar. And please don't forget to answer the survey form because that will really help us a lot in improving our future webinars. So check if we have questions here. Yes, sir, you can get the PDF file. We'll send it to you in 2 days' time. So maybe we can give them at least 1 to 2 minutes to type in their questions if they have. Or you can also send us an email if you have. If you want, you can send us an email and we'll answer it for you through email. So we have here questions. How about if we measure ground resistance with Megger DET24C? Yes, let me answer the question, the other question. Do this webinar has certificate? Yes, sir, we will send it in 2 days' time. So when we talk of DET24C, we are doing a, if I'm not mistaken, so maybe this is the clamp, right?
Yes, Michael, state close method.
Yeah. You want to answer this one?
Yeah, still possible, especially for the site that's not possible to attach the rod. But please keep in mind that this method is not good accurate just for go-no-go measurement. So if you after you get measurement from DET24C or with the clamp method, if you see something result too high, maybe still recommend to use the other method that has more accurate. Yeah, but this is only optional method. I mean, yeah, in case you not possible to attach the rod in your system. Yeah.
Yep, I agree with Sumedi because when you do the clamp method, you don't you I mean you are looking at the different loops. So let's say for example you have another loop for grounding resistance, then the current will pass through it, and maybe you are measuring a different loop and not really the ground resistance loop. So when you do this clamp method, you need to disconnect some other loops, or you need to make sure that the loop that you are measuring is the grounding loop, because you don't have to
Yeah.
disconnect everything on the clamp method. But that's why it is not accurate as the follow potential test, because there are lots of loops that you might miss to disconnect. So what I mean is, for example, in a building, of course, in a building, there are so many electrical grounding rods. And these grounding rods, sometimes they are connected to each other. So when you clamp on in a wrong spot, then you might get a very, very low resistance, but it is not actually the ground loop. It is only the loop of the grounding resistance rod. So make sure that you disconnect every loop that you can see that is not related to ground. Okay, so we have another question here. What is the latest earth resistance tester made by Megger? Sir, we have the DET2 third or DET2 slash 3. So that's the latest one, and I guess that is the most modern I've seen so far in the market. Okay, some more questions? Okay, so I guess we don't have any more questions at the moment. And for any of you who have further questions, you can also send us an email. And at this point in time, I would like to say thank you everyone for joining us today and hope to see you again next time. Please have a good day and stay safe. Thank you, Sumedi, and thank you, Grace. Have a
Thank you,
good day.
Michael and Grace.
Thank you,
Thank you,
Michael. Thanks,
everyone.
Amanda.
Bye.
Bye everyone.
Yeah,
Bye bye.
bye-bye.